With number 2, B, C, and D. So the way that we construct the ordered binary decision diagram is basically by taking different paths through this truth table, where we start at A and then we progress from A to B to C as we go down the tree, and then the corresponding outputs for the values of the input are the leaves of the tree. So you can see here for A equal to 0, B equal to 0, C equal to 0, we expect an output of 1. So every time an input is 0, we branch left. So we go A equals 0 to the left, B equals 0 to the left, C equals 0 to the left, and then we fill in that corresponding output 1. And then actually when we have an input equal to 1, we branch right. So the most extreme example would be all of the inputs equal to 1. We branch A equal to 1 to the right, B equal to 1 to the right, C equal 1 to the right, and we choose that corresponding output to be 1 based on the truth table. We can do a little bit more of a complicated example. Let's go A equals 0, we branch left, B equals 1, we branch right, C equals 1, we branch right, and we get an output of 0 as expected on the truth table here. Now we can notice a few patterns in this tree in order to reduce it a little bit. So the first observation is that regardless of the value of B, we get that C behaves exactly the same way. When C equals 0, the output is 1 here. When C equals 0, the output is 1 here. And when C equals 1, the output is 0 here. And when C equals 1, the output is 0 here. So in effect, this B node isn't doing anything because we get the same corresponding outputs when B equals 0 and when B equals 1. So we can remove this node and actually just take a single C node where when C equals 0, the output is 1, and when C equals 1, the output is 0. So that's the first simplification. The second simplification that we can notice is that regardless of the value of B here, C actually doesn't matter. If C equals 0 here or 1 here, both of the outputs are 0, and when C equals 0 or 1 here, both of the outputs are 1. So in fact, these outputs follow the value of B. So when B equals 0, the output will be 0 regardless of the value of C, and when B equals 1, the output will be 1 regardless of the value of C. So then we can take away these two C nodes, and we produce the reduced ordered binary decision diagram here, and the corresponding output logic equation can be determined by basically taking the paths through the tree that produce leaves of 1. So for A equal to 0, C equal to 0, we get a 1. So that's where we get this not A and not C term. And when A equals 1, B equals 1, we get an output of 1, and that's where we get this A and B term. And so going down the tree produces ands, and actually branching off different parts of the tree produces ors. So we can see going down the tree here, we and not A and not C, and we and A and B going down the tree here. But since we've branched from A to those two different paths, we or them together. Now we can produce the circuitry to implement this logic by basically flipping the tree upside down, and for each input that we encounter on the tree, using NMOSes with the inputs equal to 1 and equal to 0. So for input A, we would expect to see two branches with transistors with gate inputs A and not A. So we can see here from this current source, we branch off two different ways, and we get A and not A as gate voltages on two different NMOSes. And you can continue this pattern. Each time you branch, you hit a C, you're going to branch into a C and not C, which you can see actually here. We get the C transistor and the not C transistor here branching off of not A. And then correspondingly for A, we see a B and not B transistor. We're going to take this not out as the outputs that produce 1 in the tree, and this output as the outputs that produces 0 on the tree. So we can actually go through the circuitry here. For a not A input and a not C input, we're going to get to an output of 1, and indeed you can see on the decision diagram that that is the case. And then you could kind of do that for each path in the circuitry. One last thing that I'll mention is that the reason this works is because let's say that A equals 0, C equals 0, then not A will be a 1 and not C will be a 1, and these will both of these transistors will act as shorts. So we'll create a path from VDD through R to this output node, through not C transistor, through the not A transistor, all the way down to ground, and that will in effect pull this output node up to VDD through the resistor. So that's how that works. The last question that we have to go over is question number 5, and that's concerning, the first question is, why does adding a bit to the address of memory increase the number of addresses by 2, or by a factor of 2, rather. And so that's because each time you increase an address bit, you're basically taking a higher power of 2. So let's say you have 3 bits of address, that's 8 total address values, but then let's say you add another bit. For each possible value of that 4th bit, so a 0 or a 1, you still have 8 corresponding address bits that you can change to be 8 different values. So then you can change the 4th bit twice and have 8 individual values for the first 3 bits for each of those each of those values for the 4th bit. So that's 8 times 2, 16. That might have been a pretty bad way of explaining it. But so that's why we have double the amount of addresses in memory for each increasing address bit. The reason this doubles the length of the bit lines in the memory is because for a given bit line, call it bitline K, wire in memory, that connects to all SRAM cell bit Ks for each memory address. So let's say wireline 0 connects to each SRAM cell that represents bit 0 in every address in memory. So when we double the number of addresses, that bit line actually has to connect to double the amount of SRAM cells, and so it doubles in length correspondingly. So let's take a look at what that does to the delay through that wire. So based on the distributed model of the wire, we actually obtained, let's say by default, the wire in the address before we add, or before we double the number of addresses in memory, let's say that it has n resistor capacitor pairs in its distributed model. We already determined that this produces a delay of CR/2. Now let's say that we then doubled the length of the wire. So now we're going to have 2n resistor capacitor pairs on the wire, right? Because we doubled the length. So we can take this part of the diagram to be the first n resistor capacitor pairs, and this to be the second set of n resistor capacitor pairs here on the right. So if we start to do Elmore delay for this wire, we get, for the first capacitor, we have to go through R/n, the resistor R/n here, and then for the second capacitor, we have to go through 2 resistors, and then all the way up to the nth capacitor, we have to go through n resistors. Then we have to continue on because we doubled the length. We now have to go through n plus 1 resistors to get to the next capacitor, n plus 2 resistors to get to the next capacitor, and then eventually when we hit the 2nth resistor capacitor pair, we have to go through 2n resistors to get to that capacitor. So this is how we build up the expression initially. We can take C/n common from each of these terms and factor it out, which is what leaves us with all of these R terms on the inside. Again, they all have an R/n common, so we can factor that out along with the C/n. And that leaves us with the sum 1 plus 2 plus 3 all the way up till 2n. And based on the formula for the sum of the counting numbers up to 2n, we get this expression here. You basically take the product of the number that you're going up to, which is 2n, and you're multiplying it by that number plus 1. So 2n plus 1, that's where we get this product, and then you have to divide by 2. And we also did CR/n squared. We can't forget about that as well. So we can actually flip-flop the 2 out of the parentheses and the n squared back into the parentheses, which gets us this expression. And when we take this limit as n goes to infinity, which is what we have to do for the distributed model, and we do L'Hopital's rule twice, we're actually going to get that this reduces to 4, and we still have the CR/2. So we can actually see that this CR/2 is the original value that we had up here for the wire length n, and it's being multiplied by a factor of 4, so we can actually see that the resulting delay when you double the wire is that the delay increases by a factor of 4. So that's the explanation for number 5.